Hello everyone, myself Pavan Kumar S from IIT Madras, and I'm here gonna give a talk on the work title Mathematical Framework to Model Integrated Signaling and Metabolic Networks. Motivation and background. Biological systems use abilities to thrive and adapt to different environmental conditions and to fight against diseases. Underlying are three different networks called signaling, metabolic, and gene regulatory network, which act in an integrated manner to bring proper functioning and homeostasis inside the cell. Despite their integrated manner of action, most of the studies involve modeling and analyzing them in isolation. Hence, we try to integrate metabolic network and signaling network of a biological system. Modeling paradigm which we choose for metabolic network is a constraint-based model, which collects all the relevant metabolic information of a biological system and compiles it in the mathematical model. It collects information in form of gene-protein reaction rules, which indicates what are the genes that has to be present for a particular reaction to occur, and stoichiometry matrix, which indicates what are the participating entities or metabolites in a particular reaction and their respective stoichiometric coefficients, and constraints, which could be environmental or thermodynamic constraints, which indicates what are the maximum and minimal possible flux values that has to be taken by a particular reaction. So here, for example, say the lower bound of a negative value indicates the reaction is reversible reaction, and the zero indicates the reaction to be irreversible reaction. And the paradigm which we choose for a signaling network is dynamic model or ordinary differential equation based model. Here, the information which we get from the model is time versus concentration profiles of each and every signaling entities. And to simulate them, we have to integrate using a solver, provided the initial conditions for the each and every molecules in the model. So we developed a framework that integrates these two modeling paradigms, which represents the two different networks of a biological system. To begin with, we have to begin with a flux variability analysis, which is done on the metabolic network, which gives us min and maximum possible flux values of each and every reaction in the metabolic network, subject to stoichiometric constraints and thermodynamic constraints. Second step is to integrate the signaling network until time delta t using any solver. Now, using the results obtained from which is the final conditions of the signaling network, using that final conditions or final concentration, we have to give feedback or input to the metabolic network in terms of constraints and objective functions. Here we modify the constraints based on the output from signaling network. So for example, say if a particular signal activates a particular reaction, then we are going to modify the lower bound, and in case of inhibition, we are going to modify the upper bound. So once using these two formulas, and once it is done, the new set of upper and lower bounds will be used to simulate the metabolic network. And we simulate the metabolic network using flux balance analysis, which is an optimization problem where we are optimizing or maximizing a particular biological objective subject to stoichiometric and thermodynamic constraints. And we have to feedback or close the loop again from metabolic network to signaling network. So here the feedback which we're going to take from metabolic network to signaling network is in terms of flux values, which we obtain from step 4, which is flux balance analysis. And in case of enzyme, we will use this particular formula to modify the initial conditions of a particular enzyme E5. Or in case of a metabolic concentration, we will have the concentration value of a particular metabolite at time t using this formula. And this particular exchange flux value comes from the metabolic network's flux balance analysis. And with a new set of initial conditions, we will start simulating the signaling network. And this process is repeated until steady state conditions are arrived in signaling network. Now, using the paradigm developed or mathematical framework developed, we try to model real-world biological system of insulin glucagon signaling network and the metabolic network of a hepatocyte cell. The metabolic network of a hepatocyte cells, which we took, was around 62 reactions, which represents the glucose pathways. Two set of glucose pathways, one for glucose consumption, which are glycolysis and glycogenesis, another for glucose production pathways, which are gluconeogenesis and glycogenolysis. Similarly, for insulin glucagon signaling network, we have around 18 signaling molecules, and input to this has to be glucose concentration and amino acid and fatty acid concentration. Using this, these are the initial set of results which we are able to produce. And this is a reflection of normal phenotype where we try to simulate the modeling framework or the model integrated model framework using the initial low glucose concentration and high glucose concentration. So if we begin with some initially low glucose concentration here, which we have given as 60 mg per dl, whether our modeling integrated model framework would be able to settle down to steady state to normal condition or not. So it settles down to 90 mg per dl, and what it indicates in this case is like for a given low glucose concentration, our modeling framework should activate pathways which are glucose production and come back to the normal state. And in case of a high glucose concentration, our modeling framework should activate pathways which can consume glucose and settle back to normal by consuming the glucose. So this reflects the normal condition, normal phenotype of the biological system. What happens in case of disease phenotype? For example, if we try to deviate from the give a deviation like say increase the fatty acid by 3 folds, and in this case, in the both lower and high glucose concentration cases, the particular steady state value reduces to the normal one. And we also try to activate and deactivate this particular PAP3K AKT pathway, which has its role in both insulin resistant conditions and also in cancerous phenotype. Activation of this particular pathway leads to give a steady state value lesser than the normal one in both high glucose and low glucose concentration values, initial glucose concentration values. So this indicates a cancerous phenotype where more glucose is necessary for active protection of the biomass. What happens in case of deactivating this pathway, which is a insulin resistance or a diabetes phenotype? Here, in case the steady state value settles to above the normal condition value, both in case of lower glucose concentration and initial high glucose concentration. To conclude our work, the framework developer is able to capture the system behavior, and the framework developer is generic and can be used to integrate signaling network and metabolic network of any biological system. This integrated model network reflects both normal and disease phenotype. And in future, we are trying to integrate scaling network also into the framework and try to integrate omics data into the framework. Thank you.